Hi, I'm Matthias Beck. I'm one of the authors of Computing that Continues Discretely. And this video is the second one accompanying Chapter 6. We will go back to Chapter 2 and pick up generating function techniques to now compute arrayed polynomials, for example, for Beckhoff von Neumann polytopes. So I'm picking this up from the previous video. The Beckhoff von Neumann polytope of a given size n is the set of all doubly stochastic n by n matrices. We realize this is a polytope of dimension n minus 1 squared, and it is an integer polytope. You can see that because the vertices are the n by n permutation matrices, so they have entries all zeros and ones. And so the motivating question of what I'm doing now is to compute the volume. This is a famous question, and indeed this question is open for n greater than or equal to 11. Let me go back to the online encyclopedia of integer sequences. Here you can see the entry on these volumes. They are normalized here in such a way that this volume becomes an integer. And you can see I've been involved in one of the computational projects for computing these numbers. We already introduced last time that the arrayed polynomial of Bn is the set of all semi-magic n by n squares with row and column sum t, and so we have this counting function that we call h sub n. And so this is really what we're after. We're trying to compute the arrayed polynomial, and then the volume of the Beckhoff von Neumann polytope will follow as the leading coefficient. You've seen two examples of these polynomials. One was in the previous video. We computed h sub 3 by interpolation. And we already mentioned that it's hard to do a technique similar to this for really large n. But let me also remind you, when we computed things in Chapter 2, back then we were talking about contingency tables. We introduced some generating function techniques to compute h2. So here was sort of the setup. We had a constant term computation, and I want to pick up from here and get to some theorems how to compute a similar generating function for general n, and I will do that using the explicit example of n equals 4. So I'd like to use this general setup multivariate generating function from Chapter 2. The general theorem is copied here on the bottom, theorem 2.13. Let me remind you, so my polytope is given in a form, it looks like this. My entries are non-negative real numbers in some dimension d, and I have a linear system of equations, ax equals b. And so now I want to look at the Beckhoff von Neumann polytope for n equals 4 and write it in this form. Okay, so that means I need a 16-dimensional vector, non-negative entries, and my matrix, if I think of the first 4 entries giving me the first row, I have 4, 1, 0, and then the next 4 entries giving me the next row, and so on. So now I have 16 entries and all 4 row constraints. And so now if I go back to the column constraints, I will pick up 1 entry from the original rows, and then the next column, and so on. Okay. And then my right-hand side will be an 8-dimensional vector all once. Okay, so now we're set up to use this theorem 2.13. So it says I have to now go through the columns of my matrix. So in this case, I have 16 columns, and I need as many variables as rows. So you can see I have two kinds of rows. So I want to introduce two sets of variables for the first 4 rows of A and then the second 4 rows. So maybe I think in the book the variables according to the first 4 rows are gonna be called Z1 through Z4, and then we have W1, W4 for the next 4 rows. And so what this theorem gives you is that H4, so this is the Erhard polynomial of B4, is the constant term of, what do we have? We have 1 over 1 minus this monomial vector z to the first column. So in my new variable, this is a z1 to the first power and a w1 to the first power. For my second column in my matrix A, this is a z1 to w2, and so on. So I hope you can see what happens is I get one combination each of the 4 z variable and the 4 w variables. So this is going to be a total of 16 factors. And then I mustn't forget I have in my theorem 2.13 z to the tb. So this is a z1 to the t, z2 to the t, and so on, all the way down to w for each variable to the tth power. And you can see there's nothing special here about n equals 4, so we can play exactly the same game for any n. And this gives this following sort of starting point theorem. This is theorem 6.5, that we can compute hn as the constant term of this rational function. So we have 1 over a whole bunch of products, 1 minus zj to wk, where both j and k run from 1 to n. And then we have each of the n z variables and the n w variables to the power t. So here's the constant term expression for H4, copied from the previous page. We now get to choose an order of variable. Let's say we first compute the constant terms with respect to the w's. So that means on the outset, we still have to compute constant terms with respect to the z. So there's a 1 over z1 to the t down to z4 to the t. That will take care later. And then with respect to each w, what we have to do is compute the constant term of 1 over 1 minus z1, 1 minus z2 w, 1 minus z3 w, and 1 minus z4 w. And then there's my w to the t. But we're going to have to do this with respect to each wj. Each of those constant term computations is going to be independent, and so it's really the same computation that we're doing here 4 times. So we'll get this result to the power 4. This is a bit like when you have an integral in several variables and the integral factors. If you're in a situation where each factor sort of looks identical, you have the same phenomenon. And so now we're in familiar territory. So we'll do a partial fraction expansion. Just like we've done in chapters 1 and 2. You think about this, so our variable is w over here. So except for this wt at the end, which we're going to ignore after sort of imagining a partial fraction expansion, each other pole is a simple pole, namely a w equals 1 over zj for each of the z variables. And so this is actually a pretty easy thing to do, at least for this constant term in the center here. And once more, you can see there's nothing special about n equals 4. Exactly the same thing will happen for general n. And this gives you theorem 6.6 down here. The analogous computation of Hn boils down to a constant term computation in n variables. This partial fraction expansion gives rise to this sum over here, and you can see the w's are gone. But this is about as far as we can go, sort of in general and in theory. At this point, you're going to start computing. What does computing mean? Well, we have an n-fold sum in here that we'll have to take to a power n, quite a few terms appearing here, and then we'll compute the constant term with respect to one zj at a time. What will happen now in practice is something that you already witnessed in chapter 2. So here's the step exactly where we are for h2. And again, we've done this. When we multiplied out that square in the first line, we got 3 terms. But actually what happened is 2 of the resulting constant terms were 0. And we could realize that by choosing an order by which we compute the constant terms. By the way, on the upper right, you can also see, maybe you remember this, we also had to choose an order on the variables. So this is something we have to do globally. And in the general case, we'll have to do that for n variables. We might do a canonical choice here. But then once we've done that, and we multiply out this parentheses, here it's a square, in general it's a power n, we'll get lots of terms, but then we can compute each constant term separately. And when doing so, for each separate term, we can actually smartly choose an order in the hope that this simplifies calculations. If you do that now for n equals 4, and I encourage you to try this computation, we'll be left with just 5 terms, I claim, that we'll have to compute. All the other terms, and for power 4 there's already quite a few of them, you can realize that the constant term of each term will be 0. At any rate, once you're down to those 5 terms, you won't get around computing those constant terms. You will get this degree 9 polynomial for h4.